There are different ways of defining what is an acid and what is a base. The Arrhenius definition, which is named for a Swedish scientist whose last name was Arrhenius, is this, that an acid produces hydrogen ions in aqueous solution. So the example here is HCl. We learned to name this as an acid, and that is definitely appropriate when it is in an aqueous solution. But HCl as a pure compound is actually a gas at room temperature and would be named hydrogen chloride. It's a covalent compound. It doesn't actually contain ions. But when you put it in water, it ionizes. It does form ions. The compound itself, all by itself, does not have ions, but when you put it into water, it forms ions. And the ions that it forms are hydrogen ion and chloride ion. Because it forms hydrogen ions in water, it meets the definition of an Arrhenius base. Sorry, Arrhenius acid. Good grief. Now, hydrogen ions are highly reactive. Because I think I talked about this last week, but let's talk about this again for a minute, in case I didn't. Hydrogen atom. How many electrons? How many protons? 1. So when it becomes a hydrogen ion, we lose an electron, right? What's left? 1 proton. No electrons. A hydrogen ion is a proton. That's all it is. So protons are not real happy being alone. They are highly reactive, and they will attach themselves to something else. So in aqueous solution, what a hydrogen ion or a proton will do is it will attach itself to a water molecule. This water molecule has 2 lone pairs. This bare proton is not happy, okay? It wants a duet of electrons, and it doesn't have any electrons. But it can get its duet by coming over to water and saying, hey, can you share your pair of electrons with me? And the water's like, yeah, fine, climb aboard. So the hydrogen ion comes over here, and it's made a covalent bond with the oxygen in the water molecule. But this is a strange covalent bond because both the electrons came from oxygen. We call it a coordinate covalent bond. The oxygen is being so generous. It's like, yeah, you're not bringing anything to this partnership, but I'll sponsor you. Okay, so we got the 2 electrons, I'll share them with you, and then you can be happy. And it's not really affecting the oxygen that much. That's just kind of the, chemistry land view of it. So what you have then is H3O with a positive charge. Because this hydrogen ion came in, bringing an extra proton and no accompanying electron, and so now the whole business has a positive 1 charge. And this ion, H3O plus, has a special name. It's called the hydronium ion. So in water, hydrogen ions always associate with water molecules. You never, ever find them alone. They're either on the molecule that they came in with, or if they got separated from that because it was acidic and was producing hydrogen ions, the hydrogen ions would immediately grab onto one of the water molecules. So I think of these hydrogen ions a little bit like being like a 3-month-old baby. Okay, so this is a grown-up here, and here's the 3-month-old baby, and we're at Disneyland. Do you see 3-month-old babies laying around on the sidewalks by themselves? No, that would be pretty bizarre, wouldn't it? Nobody just puts the baby down at Disneyland. That's just dumb. You pass the baby to someone. Someone else, if you want to go ride Thunder Mountain, they won't let you take a 3-month-old baby on that ride. But you pass the baby, you have someone else hold it for you. So in aqueous solution, there are always water molecules available to hold the hydrogen ions. And that's what always happens. So we often use these terms, H plus aqueous and H3O plus aqueous, interchangeably. Because sometimes using the correct term, which is the H3O plus, just makes the equation really kind of complicated. And so it's a lot simpler to just write H plus, but we understand that actually that H plus is riding on a water molecule. Question?
In a real life application, does that matter at all? Like,
there's not really any practical difference whether you consider it to be H plus or H3O plus. It's really a matter of what are we calling it. Yeah. Because this is what it actually does. It actually is the hydronium ion, and it's never just hydrogen ions. But it's just like abbreviating something. It's like, well, yeah, we understand that there's somebody holding the baby. We're just talking about the baby. Where's the baby? The baby's here, there. Somebody's holding the baby, right? So just want to be clear on that because we will kind of go back and forth, and sometimes that's confusing. When we write formulas for acids, we write the hydrogen first, which we're familiar with. But there are some, like this one, this molecule has 2 hydrogens in it, and I think you've also probably seen this with acetic acid, which is HCH2H3O2. And you may have wondered, why do we separate these hydrogens? Why not lump them all together? Well, because it's that the first hydrogen, and there can be more than one, those are the hydrogen ions that will separate because this is an acid. An acid will not necessarily lose all of its hydrogen ions. So for this particular one, only one of the hydrogens come off. This is formic acid, HCHO2. And here is the structural formula for that. We've got carbon, double bonded to oxygen. It's bonded to another oxygen over here. And we've got one hydrogen on this carbon, and the other hydrogen, I think my screen is, something's too clean here, and my stylus is squeaking and skipping. The other hydrogen is on this oxygen. Only one of these hydrogens will come off. Only one is acidic, only one is ionizable. So this is the ionizable hydrogen. When we put this acid in water, this hydrogen comes off as a hydrogen ion and goes and hitchhikes onto a water molecule. This other one does not. Now, some of you may be wondering why. We can explain that, but that's more of a topic for organic chemistry, and we're not going to go there today. So when we write formulas, the ionizable hydrogen is first, and any other hydrogens are, we just think of them as any other element, just going to stay put. So bases. The Arrhenius definition of a base is that it produces hydroxide ions in aqueous solution. So here's an example, sodium hydroxide. Sodium hydroxide is an ionic compound, and when we put it in water, it dissolves into sodium ions and hydroxide ions. It produces hydroxide ions when you dissolve it, and so it is considered an Arrhenius base. If we have molecular compounds like methanol, we may look at this formula and say, oh, that's got an OH in it, that must be a base too. But this is a molecular compound, not an ionic compound. So the Arrhenius definition of bases really just applies to metal hydroxides, ionic compounds. When we have a molecular compound, and we can identify this as molecular because there's no metal ions in it. It's carbon, hydrogen, oxygen, non-metals. So that's going to be molecular. Using this Arrhenius definition, we see that acids and bases combine to form water, and this neutralizes, they neutralize each other. So the Arrhenius acid produces hydrogen ions in solution, which we understand are riding on the water molecules, and the bases produce hydroxide ions. Well, if you get a hydrogen ion and a hydroxide ion together, they make a water molecule. And this is more stable and a better situation for this hydrogen ion than riding on, piggybacking on a water molecule as a hydronium ion. And so it will do this if it's able to. So the Arrhenius definition helps us to understand a lot of acids and bases and how they react. But there are some bases, some substances that act as base even though they don't have hydroxide ions in them. And so the Arrhenius definition doesn't help with that. It also doesn't work with non-aqueous solvents. So it works great in water, but it doesn't work good in like hexane or something. So another definition was developed to explain these other phenomena, and this is the Brønsted-Lowry. This is named after two guys, and the definition is similar, and yet the difference is important. So an acid is defined as a proton donor. It donates a proton. Well, when we have an acid, like the HCl that we were looking at, when we put HCl in water, what happens to this hydrogen ion? It ends up going onto a water molecule and forming the hydronium ion. A hydrogen ion is a proton. So a proton donor is something that donates hydrogen ions or donates protons. So that really is very similar to the Arrhenius definition. The biggest difference comes in the definition of bases. A base is a proton acceptor. So we have something donating the proton, we have something accepting the proton. It's like the baby at Disneyland. If I'm going to pass off the baby to someone, there has to be someone to take it, or there's no transfer going to occur. So the acid is the one that hands off the baby. The base is the babysitter who accepts the baby. So base, babysitter. What does the babysitter do? The babysitter accepts the baby. The base accepts a proton. Okay? And this applies to a much wider range of acid-base phenomena. So it explains a lot more things. The focus here is on transfer of hydrogen ions, protons, from the acid to the base. So here's HCl. When we put HCl in water, it acts as a Brønsted-Lowry acid because it donates this proton to the water molecule. We end up with the hydronium ion, and what's left over is the chloride. This is what's left from the acid after it has donated its proton. So this just describes better what's actually happening. So this is the donor. This is donating the proton. Who is accepting the proton? The water. So here, the water would be said to be a base because it's accepting the proton. So we've always got something donating and something else accepting. Ammonia is a base, but it doesn't have any oxygen in it. And so you could look at that from the Arrhenius definition and say, how does that form hydroxide ions in solution? It doesn't really explain what's going on there. But ammonia is a Brønsted-Lowry base. When you mix ammonia with water, the ammonia accepts a proton from the water, acting as a base, forming ammonium ion. And when the water donates, acts as an acid and donates a proton, we get hydroxide ion. Yes, question?
So the water is the donor in that particular instance?
Yes. Yeah, in this situation, water is acting as the acid, donating the proton to ammonia, which is accepting it and acting as a base. Yes?
Water acts as an acid or base, but it's not considered an acid or base.
Yeah, water's pretty cool stuff. Water can act as an acid, or it can act as a base, but when you have it all by itself, it's neither. So this donating and accepting always occurs together. And I kind of jumped ahead on this, but here we have everything all labeled out. So here's the HCl acting as the acid. It's donating a proton to water acting as the base. When we have ammonia and water, now the water is acting as the acid and donating the proton to the ammonia, which is the base. And so we have a special word for this behavior of water, amphoteric. Amphibians, where do they live? Frogs. They live in the water and on the land, right? They don't just live in water like fish do. They don't just live on land like cats do, right? They go back and forth. An amphibious vehicle can drive on land or on the water. So ampho has to do with a duality. So amphoteric, and water's not the only substance that can act like this. But an amphoteric substance is one that can act as an acid or a base. Okay? And, you know, this illustration with the baby, we can carry it to that as well, because you may have a child and you could pass that child to someone so that you can go ride a ride, but you might also be a babysitter for your friend and take care of their child, right? And so you could do both. You could go both ways. What if we take this equation, and this is an equilibrium, and we're just going to flip it around. So we're going to write the NH4 and we're going to write the products of the previous example as reactants, and then the reactants as product. And so essentially we're looking at the reaction going the opposite way. The ammonium ion is donating a proton to the hydroxide ion. So the ammonium is acting as the acid, and the hydroxide ion is acting as the base and accepting it, and then you'll get ammonia and water. So there's a relationship between the ammonia and the ammonium ion. This acts as an acid in that it can give a proton to something else. This is a base because it can accept. So this is what we call a conjugate acid-base pair. One is the acid, one is the base, but the only difference is who's got the proton. Do you have the proton? Then you're an acid because you could hand it off to someone. If you don't have the proton, you're the base because you could take a proton and accept it from someone else. So they're called conjugate acid-base pairs, and they are related to each other just by the transfer of a proton. So, conjugate acid-base pair, any two substances related to each other by the transfer of a proton. I'm just going to write out some examples here. So, H2O and H3O plus. This is probably coming up in a later slide, and I'm just jumping the gun, but I seem to like to do that. We could ask questions like, is this a conjugate acid-base pair? And the way you would answer that is you look at these formulas and you're looking to see, is the difference an H plus? So this one has 2 hydrogens, that one has 3. So the difference in the formulas in terms of the number of atoms of each element is just 1 hydrogen. And then this one has a positive charge, that one has a negative, not a negative, no charge. You just start down this sentence and it's going off a cliff. Crash. So from here to here, we could get there by adding a proton to this one. And that would explain the charge and the number of hydrogens. And so this is a conjugate acid-base pair. How about... My stylus is squeaking. My goodness. How about those two? This has 2 hydrogens, 1 sulfur, 4 oxygens. 1 hydrogen, 1 sulfur, 4 oxygens. Same number of sulfur and oxygens, the difference is in 1 hydrogen, so that's a good sign. And we would get from this one to that one by adding a hydrogen. Does that explain the charge difference as well? It does. So that is also a conjugate acid-base pair. So in this equation again, the ammonia acts as the base and accepts the proton, and then it becomes the conjugate acid. Here the water is acting as an acid, it's donating a proton, acting as an acid, and then it becomes a conjugate base. So the acid becomes the conjugate base by acting as an acid, by donating its proton. The base becomes the conjugate acid by acting as a base, accepting the proton. So this is the conjugate acid-base pair, ammonia, NH3, and NH4+. And this is also a conjugate acid-base pair. The difference between them is a proton, and that's all. So in each of these reactions, identify the acid, the base, the conjugate acid, and the conjugate base. So usually what we mean by that is the acid and the base will be the reactants, and then the conjugate ones will be the products. So what's happening here? Here we've got C5H5N and H2O, and then we see what happens to them, and we're looking for hydrogens moving. So this guy has the most in common with this one, right? Did it gain a hydrogen or lose one? It gained one. Now it's got H here at the end, H+. So that makes that reactant an acid or a base. It accepted, it's the base. So this is the base. Because bases are like babysitters, they'll take the baby. This is the base, it accepted a proton. That means the other one must be the acid. And we look and we see H2O became OH minus. It donated a proton. So this is the base. When it accepts the proton, now it becomes the conjugate acid. It's a long word. So that's the conjugate acid. They are related intimately, if you will. What's a conjugal visit in prison? Yeah, they let the spouse come in and spend time with the incarcerated person. Conjugate, intimate, okay? So these two, the only difference between them is a hydrogen ion. So then this guy must be what? The conjugate base. So let's look at the second one. Which of these is acting as the acid? The HNO3. This is acid. Because we see it went from HNO3 to NO3 minus. It lost a hydrogen. It donated a proton. If that one's the acid, the other one must be the base. So which of these products is the conjugate acid? The H3O plus. I'm just going to call it Ca, conjugate acid. And then the NO3 minus must be the conjugate base. You see how I'm doing that? This is the sort of question that could be asked on an exam. I give you an equation like this and say, which one is the conjugate base? Okay, the conjugate ones are always products. And so you just identify them. Well, this one was the acid because it donated a proton. Therefore, what's left of it is the conjugate base.